Any questions?
ETA on the test feedbacks.
It should have been today. I left my spreadsheet at home, where I put all the numbers. So I apologize for that. So, definitely Wednesday. Yeah. There are a couple things that I was gonna do this morning that I couldn't do. Other questions? All right, so we have a horizontal beam here, sticking out this way. We need a visual image. Beam, rod, probably better wording. And to this, I have attached a mass of M. So this is axis of, we'll just call it fulcrum. Pivot point, whatever you want to call it. Below that, I have another rod sticking down there. And when I release it, this is going to come down, swing, the string is going to hit this, and the mass is going to then come over the bar. And what I want to know is if this distance, if that is length L and this is length D, what is the ratio of D to L so that the mass hits the lower bar? So if I had the beam right here, I want this to, starting from the string being horizontal, have this come around, it's going to hit the lower bar and then land on that spot. We assume that the bar is incredibly thin and the mass is a point mass. This is known as an interrupted pendulum. And it does not require any knowledge of pendulums at this point. So one thing that we need to do is figure out physically what's going on, because at some point, thus bringing it up now, it is a conservation of energy problem until it hits the bar here. Then it's going to, well, it's still a conservation of energy problem, but at some point, it is going to, the tension of the string is going to drop off to close enough to zero. So there's going to be some point over here. There's going to be some point over here in which the string is no longer tight. At that point, it becomes a projectile motion problem. So let's take it piece by piece. If this is the point at which, so let's actually give an angle here. Theta. If that, when it hits that angle theta, the rope becomes slack and it becomes a projectile motion problem, what do we know? Or actually, what do we know all along here? Actually, all along there. Badly worded, but hopefully. What can you tell me about the path of the mass up until it gets to that point?
Should the distance distance it is from the fulcrum stay the same?
It'll stay the same from that until we get to here, and then it'll stay the same from that. So if an object's basically staying the same distance away from something, from some point, what kind of motion is that?
Centripetal.
Yes. So at this point right here, and why don't we give it a label? We'll call this point A, call that point B. So it's centripetal motion up until it gets to this point right here. At that point, it's no longer centripetal motion. So if it's centripetal motion up to this point, so then that would be the point at which the tension is zero. What forces are acting on it at this point?
Tension.
Tension is zero.
Gravity. Weight.
Yeah, okay. So we have weight acting down. Anything else?
A normal force between the object and the rope.
That would be what we would label as tension. If the tension is close enough to zero. All right, so we just have weight. However, it is still part of this centripetal motion right here. It's just at the tail end of centripetal motion. So just after, so there's a, if this is the point at which the tension is close enough to zero, then right before it is what we're concerned with. There's still centripetal motion about some central point here. So what is the direction of acceleration at that point?
Up.
Why up?
It's going up it,
It is going up, I'll agree with that. That would give its velocity as an upward component.
or the acceleration be going in towards the middle. It's just
There would be definitely a component going in towards the middle. There's actually would be two components, because one is slowing down, and at the same time it is towards the center. So we do have some acceleration going this way, and there's some acceleration going that way.
Why is it down instead of up? Kind of, it's like pointing more down. Yeah, two arrows, one
It
side.
is, we have a centripetal and tangential acceleration. It's traveling in an arc here,
Mhm.
so it's traveling in that direction,
Yeah.
but slowing down.
Okay.
So there's an
it's-
acceleration opposite the direction of movement.
Because it's slowing down.
Right,
rather than speeding
and
up.
at the same time, it's changing direction, so there's a component this way as well.
Okay.
What is this length right here?
Radius? Or radius?
Yeah, but it is a radius.
D.
Probably help if these were on the same side. All right, so this is length L right here. Length D is this distance. Technically, center to center. So what would this be? Because this is the point at which it becomes slack.
Length, or L minus D.
L minus D. So I have this thing traveling in centripetal motion up to this point right here. I know, well, the only force acting on it is weight, what is the component that is towards the axis of rotation?
tension?
Pardon?
Would it be tension?
There's no tension at that point.
The W cosine?
All right, so let's see if it's cosine or sine. So this one is, so let's draw that bigger. So that would be the axis of rotation. This is the point at which the tension goes off to zero. Weight is the only force acting on it. That angle is theta. I have some component. Excuse me. Peanut sometimes does that to me. I was having year-old peanuts. Probably not a good idea. All right, this is theta. That's a 90-degree angle there. What would this angle be? Yeah. So I'll label that as theta prime. So theta plus theta prime is 90 degrees. So the adjacent side here. What is it in terms of? Excuse me. I'm just let it keep recording. I'll be right back.
No.
I need to study.
I can stay.
I haven't studied at all. And I know I'm not good at it.
I don't remember
Should we
that
were
before.
assign like the map, those like homework, so like those things, like maybe the classes, like help. Not saying so much work, you know?
I feel like I learned less if I do master science versus studying in terms of like time.
I guess I learned good with like,
Master science should be, I know it, and then I'm gonna apply it. Not now. I'm trying to look at my notes on how to do it.
well, what about, those like homework solution things?
Sorry,
That just gives you practice with like different, that makes time, right?
This is about what's practice.
Yes.
All right, so what would this be, this length be? Or if it helps, what is this angle down here?
Theta.
Yeah, that would be theta. So this component would be,
Cosine.
90 degrees.
Oh, the angle? Oh,
That-
90.
the hypotenuse of W, and this small triangle right here.
Oh, wait, no, sine.
You say sine or cosine, I have two angles. Sine, it's cosine of one and sine of the
Oh.
other.
W sine theta.
Alright, so this would be W sine of theta. So I have one relationship here. I know that W sine theta is going to be equal to mv squared over r, where r we've established is L minus D. We could take that one step further. W, we get mg sine theta, which is mv squared over L minus D, and the mass cancels out. Now, in reality, the mass should not make much of a difference. We assume that the string is massless. The problem would be that the larger masses will be larger in size, and that becomes more difficult in terms of how well we nailed it. So I now have this idea that the speed squared is equal to L minus D, G sine theta. Now we can keep L minus D as is, or we could come up with a single letter for that and then just substitute back at the end when we need to. I'm going to keep L minus D for now and hopefully not make another mistake. I also know one other thing here. I can figure out if I know this is L minus D, I know what this length here is. So again, looking at that triangle, I know that angle is theta, the hypotenuse is L minus D. I need to figure that out. So what is that?
LD sine theta?
With a minus in there, L minus D, or sine theta. So, we now can also figure out the speed squared at this point using conservation of energy. I know it starts at, classic black on black. There we go, all right. So, we start up here. I've got some point there, so it's gonna be swinging around at a somewhat constant radius to start with of L. At this point, the string is hit, and we have a new radius of L minus D. And what I need to figure out is the height at this point. Again, this is the point at which the tension goes off to zero. I need to figure out the height at that point so that I can use our classic conservation of energy formulas. Well, I know that height there, that length right there is, we just did that L minus D. It's an L minus D sine theta. Where that angle there is theta.
Is that, with both those triangles combined, is that a 90-degree angle?
Which, that's 90 degrees there.
Oh, okay.
Well, if we're gonna do height, we need to figure out where h is equal to 0. Where do you want to make h is equal to 0?
Would it make sense for it to be at the bottom?
Maybe. Alright. So h is equal to 0 there. So what is the initial height?
Where's the
L.
L. It's the length of the string there. Because if the initial height is how would be that distance right there, and that's just the length of the string. The final height,
D minus L minus D sine theta.
D minus L minus D sine theta. That would be that distance there.
Okay.
So if h is equal to 0 at the bottom,
Is the mass is it going to land on the bar?
yeah, we'll assume that the center, that this point mass will land at the center of the bar. Alright, we established h is equal to 0 there. So I'm trying to find that height. I know this height right here. That's L minus D sine theta. What is this height right here?
L minus D.
Yeah. So my final height is going to be L minus D plus
Plus OD.
L minus D sine theta. So now if I want to do conservation of energy, well, let's think about the forces involved here. I have tension in the string as it's swinging down. Why is the tension in the string not doing any work as it's swinging.
There's nothing like pulling on it, so it's just at its natural.
Not the reason why. Even if there was something increasing the tension beyond what was necessary for this one mass, it still would not be doing any work.
Because there's no movement in that direction.
That is why. Because at, say, at this point right here, the tension is in that direction, but the movement's in that direction. The tension is always towards the center, and the movement is always perpendicular towards the center. And so therefore, the tension, the work by the tension, is zero, because the tension is perpendicular to the displacement at that moment. The only other force involved here besides tension is weight, which is a conservative force. Energy is conserved. So energy initial equals energy final. The initial energy, we have the initial height is, so it's all kinetic, all potential at that point. Well, go ahead and write out the form, slightly formalized. We've got the initial mechanical energy equals the final mechanical energy. I'm about to ask that question. So if you need to look it up real quick, please do. What's the formula for kinetic energy?
1/2 mv squared.
That was nice. What's the formula for potential energy?
Depends.
The one associated with weight. So what is the formula for potential energy associated with weight?
Is that MGH?
That's the one.